In this section, I want to talk briefly about unique factorization in other integral domains than the integers. So let's start with the concept of a unit. So if I'm in a ring with unity element 1, then an element u is called a unit if it has a multiplicative inverse in the ring. So multiplicative inverse means there exists some v such that v times u and u times v both equal 1. So I'll use the standard notation that v is u to the negative 1 for a multiplicative inverse. Okay, so what are the units in the ring of ordinary integers? This would just be plus or minus 1. These are the only integers whose reciprocal is again an integer. If we go to the Gaussian integers, we still have plus or minus 1, but now we have as well plus or minus I. Indeed, the multiplicative inverse of I is minus I, and the multiplicative inverse of minus I is plus I. And these are the only elements that have multiplicative inverses that are Gaussian integers. Indeed, if you took an a plus bi inverse, and we just multiply top and bottom by the conjugate, this would be a minus bi over a squared plus b squared. So the only way this could be a Gaussian integer is if this denominator was equal to 1. It's certainly positive, so it would have to be equal to 1 to avoid fractions, and that would imply that b is 0 and a is plus or minus 1. So that would give us these two Gaussian integers right here, or that a is 0 and b is plus or minus 1, giving us these two Gaussian integers. So these are the only units in the Gaussian integers. In a polynomial ring over a field, the question is, when is the reciprocal of a polynomial again a polynomial? Well, that can only happen for a constant polynomial. So the answer here would be non-zero constants, or non-zero constant polynomials. In general, if you take the reciprocal of a polynomial, we call it a rational function, and it would not be an ordinary polynomial. Okay, next let's talk about primes and irreducibles. So in algebra, these words have different meanings. So in particular, the word prime is defined differently than we did it for the ordinary integers. So let's see how this works. So let A be a non-zero element of an integral domain. We'll say A is composite if it can be expressed as a product of two non-units. So that's consistent with our notion of composite integer. So 12 is composite because I can write it as 4 times 3, and 4 and 3 are non-units. Next, we'll say A is irreducible if it's not a unit and it's not composite. So there's no way to factor it as a product of two non-unit elements. And we'll say A is a prime, item 3 right here, I guess, if A is a non-unit, and whenever A is a divisor of a product of two elements in your domain, then it must be a divisor of one, at least one of the two elements. So A divides B, or A divides C. And notice both of these concepts hold for primes in the integers. So every non-zero element of an integral domain is either a unit, a composite, or an irreducible. Okay, what are the irreducibles in the integers? Well, these are just the ordinary primes, so 2, 3, 5, 7, 11, 13, etc. But in the algebraic definition I just gave, they would include some more values. They would include -2, -3, -5, -7, and so on. All of the negative ordinary primes cannot be expressed as a product of two non-units. And again, plus or minus 1 would not be considered irreducibles because our definition stipulated that it should be a non-unit. What are the primes in the integers? So prime here I mean according to the algebraic definition I just gave. Well, again, it's going to be exactly the same set of objects. So it's just the set of ordinary primes, 2, 3, 5, 7, etc., and the set of negative primes. Right? We've already proven a theorem that says if P is a prime in Z, in the sense we defined in the earlier chapters, and P divides AB, then P divides A or P divides B. Right? So that means the ordinary primes right here that we saw in the integers satisfy the property that we just gave for the algebraic definition of a prime. And non-primes, let's take a composite number like 6, is not a prime in the algebraic sense. Because why? Why does it violate this property? Well, 6 is a divisor of 2 times 3, but 6 does not divide 2, and 6 does not divide 3. So the composite ordinary integers are not primes in the algebraic sense. Okay, so in the integers, primes and irreducibles mean the same thing. Okay, so the set of all units in a ring we claim is going to be a group. So let's start with the following lemma. If U and V are units in a ring with unity, then U times V is a unit, and its multiplicative inverse is the inverse of V times the inverse of U. So this is a formula you should have seen at some point with matrices, and the proof is just going back to the definition of a multiplicative inverse. So if you take U times V and I multiply it by V inverse U inverse using the associative law, we can regroup the parentheses. V times V inverse is the identity. The identity goes away, and then U times U inverse again is the identity. And this property works in both directions. Also, V inverse U inverse times UV, like that, is V inverse U inverse U. V, and again we get 1. Okay. So we've shown that this quantity on the right-hand side satisfies the definition of a multiplicative inverse of U times V. So QED. That's exactly what we needed to show. So here's the theorem then. Any ring with unity in the set of units is a multiplicative group. So we just have to ask, okay, what does it take to show something's a multiplicative group? We have to show the set is closed, etc. Let's give a name to the set. So let's let capital U be the set of units. in ring R with an identity element 1. So why is U closed under multiplication? So U is closed under multiplication. Well, that's exactly what our lemma just proved. If U and V are units, and I take the product, I get a unit. Two. We need to have an identity element. Well, 1 is a unit. And 1 is an element of R. And 1 is a unit. Why? What's the reciprocal of 1? It's just itself. So 1 is an element of U. 1 is in R because I'm assuming we have a ring with unity here. So this ring is R right here. And what's the third property a group needs? Every element has to have an inverse with respect to the binary operation. So my binary operation is multiplication. So if U is in U, then what's going on here? Well, then it has an inverse, and this is also in U, since the inverse of U inverse is just U. Okay, so we have all the properties required to be a group. The associative law is inherited from the ring R itself, so we don't even need to mention that. We can put that in here. Associative law comes from R. Okay, I claim that in any integral domain, primes are always irreducible. In any integral domain, primes are always irreducible. So let's let P be a prime in an integral domain R. Okay, I want to prove that it's irreducible. So let's suppose we can factor P. Suppose P equals U times V for some U V in R. So my goal is what? I want to prove that P is irreducible. That means that whenever you can factor it like this, one of these two elements, U or V, has to be a unit. Okay, so that's my goal. Put that on our side. U or V is a unit. And I need to use the definition of prime at some point here. So P is a prime. That means if P is a divisor of a product of two things, then it divides one of those two things. So what is P a divisor of here? Well, this equation tells me that P times 1 equals U times V. So we're in an integral domain, so it has a multiplicative identity 1. And that would tell me that P is a divisor of U times V. Which implies that P divides U or P divides V, since P is a prime. Okay, it's perfectly symmetric. Let's assume P divides U without loss in generality. So P times x, let's say, equals u for some x in R. And now let's come back to our starting equation. P equals P equals uv, then would imply that P, and substitute this in for u, is px times v. Well, what is that going to mean? Let's rewrite it like this. P is P times xv. Aha! We're in an integral domain. We have a cancellation law, so I can cancel the p's on both sides. And I get 1 is x times v. But that's an equation that tells me both x and v are units. Well, x is irrelevant, so v is a unit. Aha! That's exactly what my goal was. We wanted to prove that if P is a product of two things, and one of those two elements is a unit. QED. Unfortunately, the converse of this statement is not true. Irreducible elements need not be primes. So I'll give you a homework problem where you can carry out the details, but let me just point out what the problem is. So let's consider this ring here. It's like the Gaussian integers, but instead of adjoining the square root of -1 to the integers, we adjoin the square root of -6. So it would be all complex numbers of this form, a plus b times the square root of -6, where a and b are integers. Okay, and that's clearly a ring. It's closed under multiplication and addition. And in your homework, you're going to show that the number 2, which is an element of this ring, is irreducible, but is not a prime. And you do it by showing the following. You're going to show that 2 is a divisor of this product right here. So these are two elements in this ring, but it is not a divisor of either one of these two elements. So 2 is not a prime. So here we have an example of an irreducible element not being a prime. And there's lots of examples of this type that you can concoct. Okay, next let's talk about associates. So two elements of an integral domain are called associates, written a tilde b if a is u times b for some unit u. So a and b differ by a multiple of a unit. Lemma. If a is a divisor of u, where u is a unit, then a itself is a unit. And this is in any integral domain here. Integral domain. Proof. Okay. Well, a divides u means that a times x equals u for some x in my ring R, let's say. And I want to prove that a is a unit. Okay, so u is a unit. So since u is a unit, there exists some v in your ring with uv equaling vu equaling 1. Well, we're in an integral domain here, so multiplication is commutative. I really don't need to stress this two-directional thing right here. So then, how do I get a multiplicative inverse of a? Well, if I multiply both sides of this equation by v, we have ax times v equals u times v, and that equals 1. And so by the associative law, a times xv equals 1, and therefore a is a unit. We have a multiplicative inverse x times v. Since xv is an element of my ring. Okay, any divisor of a unit is a unit. Okay, next let's look at divisors of irreducible elements. So suppose P is an irreducible, then I claim its only divisors are units and associates of P, which is exactly what we would want it to be, that irreducible elements should not have any non-trivial divisors. And that's just basic definition on part 1. Is there anything to write down there? So if P is an irreducible, let's suppose U divides P, where P is irreducible. Well, that means that U times V equals P for some V in your integral domain that we're working in. So all of these were in are as some integral domain that I'm working in. So what do I want to do? I want to show that U is either a unit or an associate of P. Well, if U times V equals P, then since P is irreducible, either U or V is a unit. Since P is irreducible, this is really a trivial result. So if U is a unit, then it's a unit. And if V is a unit, then U is an associate of P. So if V is a unit, an associate of P. Okay, part 2. If P and Q are irreducibles and P is a divisor of Q, then P is an associate of Q. So P tilde Q. Well, P divides Q implies by part 1 that P is an associate of Q. Yeah, because P is a non-unit. Yeah, we can be more formal here, I guess. So you say, let P, Q be irreducibles. In particular, they are non-units. Right, that's part of the definition of irreducible, is that they're not units. Okay, so P and Q are irreducible. And suppose P divides Q. Well, then by part 1, P is a divisor of Q, so it must either be a unit or an associate of P, but it's not a unit. So then by part 1, P is an associate of Q. And that's all there is to it. Okay, so I just want to be real brief talking about unique factorization in other domains. We just needed the language in order to state the results, and we'll just kind of outline without going into the details of the proofs. So an integral domain is called a unique factorization domain abbreviated UFD, if every non-zero, non-unit element of the domain has an essentially unique factorization into a product of irreducible elements. So A is P1 times P2 ... times Pk, where P1 through Pk are some irreducible elements. So by essentially unique we mean the following, that if A had a second such factorization, say P1 prime times P2 prime ... times PL prime, then L must equal K, so you must have the same number of irreducibles, and there must exist a permutation sigma of 1 through K such that P sub I is U sub I times P prime sub sigma of I, for some units U sub I. So in other words, the primes in the two factorizations are just a permutation of one another up to unit multiples. So all of these PIs are associates of the PIs in the other factorization. So for instance, if I'm factoring the number 30 in the ordinary integers, the standard way to do it is to say it's 2 times 3 times 5. Now I could also write it as 3 times 2 times 5, or 5 times 2 times 3, etc. Or more generally, we could introduce negative signs. I could say it's negative 3 times negative 5 times 2. These are again our primes and irreducibles in the algebraic sense, but note that they differ from the original factorization up to unit multiples. So the 3 corresponds with this, the 5 with that, and the 2 with this. So again, we regard this as the same factorization into irreducible elements. And you would have all the possible permutations here as well. You could have a plus 2 and a negative 3. So you could have the 2 negative signs on any 2 of these elements. So you have all sorts of different factorizations with plus or minus signs, all being considered the same factorization. Okay, so in this language, the fundamental theorem of arithmetic just says that the set of integers is a unique factorization domain. Now, the proof we gave for the fundamental theorem of arithmetic actually holds identically for any Euclidean domain. And so it's not hard to prove that any Euclidean domain is a unique factorization domain. And what are some of the important examples of Euclidean domains we've seen? The Gaussian integers and any polynomial ring over a field F. So these would both be examples of unique factorization domains. But keep in mind, in the Gaussian integers, you have more units. So when you're factoring, it's only unique up to these unit multiples. So you can multiply a given prime factor by I if you want, and you'll still consider it the same factorization. Okay, let's look at the proof for Euclidean domains. I'll just give the ideas because it really is identical to what we did for the integers. So let's recall that in any Euclidean domain, there's a mapping delta from the non-zero elements into the natural numbers together with 0. And it had this property that delta of A is less than or equal to delta of A times B for any elements in the domain. In fact, you can prove from that definition that delta of A is strictly less than delta of A times B for any non-unit B. And thus, you can prove the existence part of factorization by induction on delta of A. So how would that work? Just think about how we did the existence proof for factorization of ordinary integers. You have some base case, like 2 is a prime, something like that. And then the key step is the inductive step. So let's look at the inductive step here. So here you'd say, suppose that all elements of your domain with delta, all elements A of the domain with delta of A less than n, some given n, have a factorization into primes, or into irreducibles, let's call them. And now you want to consider an element whose delta value is equal to n. Consider now an A in the ring with delta of A equaling n. And you have these two possibilities. Either A is irreducible, in which case you're done, or A can be factored into a product of two non-units. So if A is irreducible, we're done. Else A equals BC with BC non-units. But then what can I say about the delta? Well, then delta of B is strictly less than delta of BC, which is delta of A, which equals n. Aha! Delta of B is strictly less than n. Likewise, delta of A is strictly less than n. So we can apply the induction assumption. B can be factored, A can be factored, not A. That's C right here. Delta of C is strictly less than n. So B can be factored, C can be factored, and thus A can be expressed as a product of irreducibles. So that's how the proof flows there. And then for uniqueness of factorization, you have to go through all of the steps we did for the integers. So we got started by doing the GCD-LC theorem, where we prove that the greatest common divisor can be expressed as a linear combination. And this can be done identically in any Euclidean domain because we have a Euclidean algorithm. So another way to do it is to use the fact that Euclidean domains are principal ideal domains. I'll talk about that shortly here. Okay, next, after you do a GCD-LC theorem, you prove a Euclid's lemma for a general Euclidean domain. So if D is a divisor of A times B, and the greatest common divisor of D and A is equal to 1, then D must be a divisor of B. And that follows immediately from the GCD-LC theorem. Next, you prove that primes really do behave in the same way as we did in the integers. In other words, we prove that any irreducible element is a prime. Now here I'm using the algebraic language. Irreducible meant you can't factor it, and prime means it has that divisibility property. So this was the converse statement that was not always true. But for the case of Euclidean domains, it is true. If P is an irreducible and P divides a product of two things, then it must divide one of the two. And that follows immediately from Euclid's lemma. And then finally, using induction, you prove that if P is an irreducible and it divides a product of things, then it must divide at least one of those elements. So with these ingredients, one can proceed to do exactly the same proof that we did for the fundamental theorem of arithmetic. Okay, now I mentioned the concept of a principal ideal domain, so let me just clue you in on what this is. This is a more general example of a unique factorization domain. So a principal ideal domain, which we'll abbreviate PID, is an integral domain in which every ideal is principal. So that is, it's generated by a single element A. So the notation parentheses A just means all multiples of A. So we saw earlier that Z is a principal ideal domain. That's when we prove that every subgroup of the integers is just the set of multiples of some fixed element. And there's a theorem that says if D is a Euclidean domain, then D is a principal ideal domain. So principal ideal domains are more general than Euclidean domains. And the proof of this is based on the following lemma, which again will leave the proof for homework for you to think about. So the lemma says this: suppose that I is an ideal in a Euclidean domain, and that A is a non-zero element of I where delta of A is minimal. So remember, in a Euclidean domain you have the mapping delta. You choose an element A with delta of A being minimal, and you can prove that the ideal I is just a principal ideal generated by the element A. And this follows from the division algorithm. The division algorithm, remember, is the part of the definition of what a Euclidean domain is. So you can do that as an optional homework problem if you like. So let's state without proof, and if you want to write up a proof of this for a homework, that would be fine. It's a standard result done in upper level algebra class. If D is a principal ideal domain, then D is in fact a unique factorization domain. So PIDs give us a more general class of unique factorization domains. And so we have the following chain of implications. We've got Euclidean domains, principal ideal domains, and unique factorization domains. So if it's a Euclidean domain, then it's a principal ideal domain, and if it's a principal ideal domain, then it's a unique factorization domain. And you may want to ask, okay, are there unique factorization domains more general than PIDs? And the answer is yes. You can have unique factorization domains which are not principal ideal domains. I'll give you an example right here. Whenever you start with any unique factorization domain and you look at the polynomial rings over it, that will again be a UFD. However, this is not a PID. This is a UFD, but not a PID. Again, this is standard material for an upper level algebra course, so I won't pursue it any further in this class.